only in the back for Eva's thesis defense. And you can see the title of her thesis here. She's been working a long time on various ways of interpreting seismic information from under North America and interpreting that in terms of the geology, which I personally think is a great thing to do. And before Eva starts, it's traditional to let her thesis supervisor say a few words. So Rob, I'll turn it over to you. Then you can go ahead and turn it over to Eva.
Okay, well, thank you. I won't make it long because you have so much to share with us. I'm really delighted to see so many people here, and it's true, we need a bigger lecture hall for this over the next time we do that. So we're all here to celebrate, the finishing touches of Eva's work on this very challenging topic that she's been working on. I misspoke when I just checked with her when she started, and I said 2004.
With an error.
No, it was in the Obama years. So. But those are all details. Eva has been here for a while and started off on a very challenging project. That sounded quite simple by saying, okay, we have a lot of constraints from seismic tomography, from the travel times of body waves like PNS waves, and we have a lot of information about the surface waves, but it's actually very difficult to combine them, and actually very few people have done that. So you set out to try to do that, and it was actually quite difficult to really look at the stability and get robust results, and especially if you go the next step, not just to constrain P wave propagation, S wave propagation, but also the ratio between VPVS. And that is very interesting because it typically constrains much better than VPVS alone, the constraints in composition. But it was a very difficult thing to do, and so the second act of your thesis was a little bit slower because of the challenges there, and also there was a lot of time that you spent on basically bigger institute issues with the Greater Student Council. Which was very, very good to do, and I'm very glad you did that. And there was also, of course, the benign neglect by the department head. that didn't really help at that time either. So then you got some really exciting results, a beautiful paper, and also very, very exciting results for VPVS. And I've been looking at these maps for a long time, and I thought, you try to make sense out of the geology, and very often that's done as kind of a superficial, qualitative afterthought. And I really challenged Eva to go a little bit further and say, well, it would be really good to have more quantitative integration of the geology and the petrology and the tomography. And so I said, talk to Ollie, because Ollie and Mark Bain had done a lot of work on VPVS and what it means in terms of seismic properties, but also in terms of composition. And so talk with Ollie she did, and very quickly she started working with Billy Schinover in the back, Ollie's student, on what I think became a very nice, beautiful, exemplary, joint collaboration between geologists and seismologists, and really resulting in I think a beautiful, successful attempt to really integrate the petrology into the constraints we have from seismology. And I'm very impressed by that, what you have done and managed to do in the end. It was kind of culminating in the last AGU where Billy and Eva gave kind of back-to-back presentations at the AGU, which was very well received. So very proud of your work. I'm very much looking forward to the summary of your work over all the years in the next 45 minutes. We'll take it from there. You did not introduce the committee, but I did that, so I will do that. So Vicky Royden is the chair of the committee, me as a supervisor, of course, but then Ollie and Brett Hager. And Fiona Derbyshire is joining us from far on Skype. Hi Fiona, hello. Thanks for being here.
Oh no, happy to be here.
Okay, Eva, all is yours.
All right. Thank you for the introduction, and thank you everybody, friends, colleagues, for showing up to support me today, and anybody who's tuning in via the YouTube channel. Thank you for your support. It really means a lot to me. The title of my thesis is Imaging and Interpreting Seismic Heterogeneity in the North American Lithosphere. And as Rob mentioned, I'm really interested in not only imaging the Earth through seismology, but in deciphering the meaning behind that and the geology and the Earth processes that we can understand from these images. So this is a quick structure of my thesis. I'm not going to walk through chapter by chapter, but generally I start with waves and I end with rocks. So I spend a few chapters developing and implementing inversions to find the seismic structure of the lithosphere. Then I dive into a few case studies and applying this to infer things about the geologic evolution of the lithosphere. So the format of this presentation will more or less mirror that. I'll start out by motivating the research and discussing the questions that sort of guide me. Then I'll discuss the seismic inversions that I perform and introduce those models. Then I'll describe the geochemical modeling that Billy and Ali have worked on and compare these two results. Then finally, I'll use this interpretive framework in order to answer some questions about how mantle plumes can alter the lithosphere. So I'll start with motivating questions, and I'll also give a little bit of background and explain some terminology because I know not everybody here is as familiar with geophysics jargon. So here's the Earth. The Earth can be divided into layers, and we can look at these layers either in terms of their chemistry, in which case we differentiate a thin crust, a mantle, an outer core, and an inner core. We can also describe these layers in terms of their mechanical behavior, in which case we have a rigid lithosphere, which is comprised of the crust as well as parts of the upper mantle, and a asthenosphere below that, which is viscous and over time, long time scales, convects and flows, and a liquid outer core and a solid inner core. Now I'm interested in looking at the lithosphere, and even from this sort of vertically exaggerated cartoon diagram, we can see that there's a lot of heterogeneity within the lithosphere. We have very thin regions, which tend to be beneath the oceans, and we have the continents, which the lithosphere is thicker, and there's a lot of variations within the continents of thickness and different things like topography and different ways of deformation. So I'm going to be focusing on the continental lithosphere, and particularly on regions called cratons. And cratons can be considered the cores of the continents today. They're Archean in age, which means they're older than 2.5 billion years. In fact, the oldest rocks on Earth have been found within cratons. And this map here shows some of these cratonic terrains, which is a term that basically means rocks that formed in a similar way. And they kind of cluster together in these larger regions called shields. And shields were formed mostly during the Proterozoic, which is between 2.5 billion and about 540 million years ago. So it's only really these areas in green around the peripheries of these shields that is involved in most of the deformation, seismic activity, things like that in the continents today. So I want to use seismology, which is studying the vibrations of the Earth, in order to investigate the structure and dynamics of the continental lithosphere. And I sort of have two main questions that will guide this talk. The first is, what controls seismic wave speed at large scales within the lithosphere? So this figure here is sort of a preview of some of the models that I'll be talking about later on. It's a tomographic slice at 60 kilometers depth, and I'm showing the boundaries of the United States just to guide our interpretation. And the colors correspond to the speed at which seismic waves, in this case shear waves, propagate through the Earth at this depth. So blue corresponds to waves that move quickly, and red means they move slowly. And to a first order, a lot of studies will look at this and say things that are red are warm, and that's why waves move slowly, and things that are blue are cold. However, wave speed is actually a function of a number of properties, which includes temperature, but also composition, so what minerals and which elements are present in the rock. It can also be factored or influenced by factors like the presence of melting, anisotropy, which describes variations in wave speed depending on the direction, and attenuation, which is loss of energy due to things like scattering and anelasticity. So in fact, when we look at regions such as the northern United States, which are Archean in age, we can say, oh, maybe they're fast because it's very old and cold lithosphere, but there also could be a different chemical composition because these rocks were formed very early on in the Earth's history, and we don't know if continental lithosphere was generated in the same way back then. They could also have been altered somewhere over this 2 billion year history. So we really want to be able to look at how cratonic lithosphere can be altered over geologic time. And one mechanism that will be kind of a recurring example of how to get this alteration is mantle plumes. This is a schematic of a convective upwelling coming from the core mantle boundary, which we call a plume. And there's a lot of debate in the literature about exactly what the nature of plumes are, whether they're coming all from the core mantle boundary, exactly what the composition is. I don't want to wade into that, so I'm choosing a very uncontroversial definition of a mantle plume. And that's just something that represents a thermal anomaly, but also a different composition because it's coming from somewhere deeper than the lithosphere. So with these questions in mind, I'm setting out to interpret these maps, and I use a framework that can be conceptualized like this. So a lot of seismic studies will focus on this side, where we have a waveform that is recorded at a seismic station as the Earth vibrates due to an earthquake passing through. And we can perform some signal analysis on this, get a map of the Earth, and in the case of tomography, it'll be some map of wave speeds. But we don't want to just leave it there and say this is maybe warm, but we're not quite sure. And in order to do that, we really need to understand the way that phenomenon like heat and geochemical changes interplay with one another and how that affects velocity. So we need to have a modeling side, and we choose to do this in a forward way. So we start with rock compositions and determine velocities and compare these two methods at the level of these maps of velocity. So this is the main framework for what I'll be talking about for this talk. And we choose the continental United States, firstly because it's a really interesting region. It records billions of years of Earth history, and there's a lot of tectonic problems we can address. Secondly, more practically, we also have a lot of really good seismic data in the United States. These are stations associated with a project called the US Array Transportable Array, which was run by an organization called EarthScope. And over the course of 10 years, they installed seismic broadband stations across the entirety of the continental United States at roughly 70-kilometer spacing. And this is really unprecedented high-resolution, high-quality data coverage over a very large scale. So this is really an ideal test case for developing new methods and new forms of interpretation. As a result of US Array, but also a lot of careful geology analysis and regional seismic studies, we know the lithospheric structure beneath the North American shield fairly well. This map summarizes the major provinces within the lithosphere we'll be looking at. In the blue are these Archean terrains. We can resolve the southern part of the Superior Province. This is the largest of these cratonic terrains. We can also find the Wyoming Province. And subsequently to the Archean, the North American continent continued to be built through the addition of several large provinces in sort of these elongated parallel geometries. And these are the Yavapai, the Mazatzal, and the granitoid rhyolite province. And they behave more or less cratonically, particularly in the eastern part. So stitching together all of these pieces are these yellow regions, which I call origins. And this basically just means mountain belt. So think of these as the Himalayas today. They're these mountains that arise from the collision of giant terrains. Finally, there's this feature in red in this arc shape, and this is the Midcontinent Rift, or MCR. And I've labeled this as an LIP, which stands for Large Igneous Province, and it's basically just a big collection of volcanic rock that was in place very rapidly. And this was formed about 1.1 billion years ago. So this is the basic structure of the features that we'll be looking at. And now I'll just give a brief sort of introduction to the chemistry of the mantle that is relevant to this work. So this is now a vertical section from the crust through the lithosphere to the asthenosphere. And again, we have a mantle plume sort of driving alteration. The lithosphere is what we call ultramafic. It's dominated by the elements silicon, magnesium, iron, aluminum, sodium, calcium. And I'm mainly going to focus on silicon, magnesium, and iron during this presentation. The most dominant rock in the mantle, at least in the lithosphere, is something called peridotite. And the dominant mineral in peridotite is olivine, which has the formula Mg or Fe2SiO4. And the parentheses just mean that there's two end members, one with iron, one with magnesium, and they sort of mix together in a solid solution. And whether or not iron or magnesium is more or less prevalent, this can tell us about the history of the rocks we're looking at. And one way to vary the amount of magnesium and iron is through melting. So we can imagine this plume sitting below the lithosphere is heating the rock above it, and if the rock gets hot enough, it'll melt. And we're not going to find, a giant pocket of melt in the lithosphere where the entire rock melts. It'll be the components that have the lowest melting point that turn into liquid. This is called partial melting. And the iron end member of olivine preferentially melts first. So that will be removed from the system and percolate upwards. And the solid that's left behind will be relatively depleted in iron or enriched in magnesium. We call that the residue. And now the melt that goes upwards through the system could go all the way up and be released at the surface in volcanoes, or it could be stuck somewhere within the lithosphere, in which case it freezes there and is just present as a relatively enriched pocket. And this is known as underplating. The second process that we want to consider is metasomatism, which is chemical changes in the rocks due to the reaction with fluids. In this case, fluids coming from the plume. And metasomatic reactions can take a number of forms depending on the composition of the fluid, the composition of the lithosphere, but a very common fingerprint of these sorts of reactions is the formation of a mineral called orthopyroxene. And this is a chemical formula, and it's richer in silicon than olivine. So these pockets will be, if they exist, these patches of altered lithosphere will be observable as relatively silica-enriched material with the effects that has on the seismic wave propagation. So that wraps up all of the introductory material. So I'm going to leave chemistry behind for a little while and think about waves and introduce the seismic inversions that I perform. So a reminder, now we're looking at this right-hand side of the diagram. So the way that I make images of the Earth is through seismic tomography. And a lot of you might have some sort of intuition for what this is because it's very similar to medical imaging. In fact, I like to tell people that my research involves taking CAT scans of the Earth. So mathematically, and this is the most complicated math that I'm going to talk about today, we're looking at velocity equals distance over time. So if we know where a wave travels through the Earth, and we can figure out when a particular phase arrives at the station based on looking for a particular wiggle, then we can work backwards to infer how fast it was traveling. And we can make many observations from many earthquakes at many stations and form a large matrix problem of the form GM equals D, and that's just a formulation that we use very frequently in geophysics, where G is some operating matrix based on physics, M is our model of the Earth, and D is the observable, in this case, information from seismic records. Now, the joint inversion that I do is an inversion of body waves and surface waves. So body waves propagate through the interior of the Earth, and these can either be P waves, which are sensitive to compressional velocity. And in P waves, the oscillation of particles is along the direction of wave propagation. They can also be shear waves, or VS, in which case particle oscillation is perpendicular to the direction of propagation. And VS is always slower than VP. So body waves, as I said, are good at sensing deep within the Earth, but there's a problem, and the problem is if we can imagine standing at one of these stations very far away from the earthquake, the waves will be arriving nearly vertically below you, so it's really hard to tell whether an anomaly that it's encountering is occurring right below your feet or 100, even 200 kilometers depth. And the scales of lithosphere, so the depth of the lithosphere is generally about 100 or 200 kilometers below the continent. So it's really important that we have better vertical resolution. And we can do that by adding Rayleigh waves. which are a type of surface waves, and particles oscillate with kind of a complicated elliptical motion. And surface waves have a property called dispersion, which means that different frequencies of vibrations will be sensitive to different parts of the Earth, or different depths within the Earth, and they'll travel at different speeds. So we can measure surface waves at different frequencies and get a good sense of how the vertical structure is varying. And this is a very nice complement to body waves. So we can put both of them in one inverse problem and hopefully get improved 3D resolution at lithospheric scales. So this describes how we do this joint inversion. For body waves, we use ray theory. So we approximate propagation as an infinitesimally thin layer or ray that goes through the wavefront. And the formulation of these has been known, and it's been used in global tomography since the 1970s, where the rays follow some arc path from source to receiver. And in this case, G just describes their length along this path. Our Earth model, is notated as delta S sub S, which just means perturbations in the shear wave slowness relative to some reference model, hence the delta. And slowness is just 1 over velocity. And our observable is delta T, that's the perturbation in travel time, also with respect to some reference model. So body waves are a nice sparse linear problem that we can invert for very efficiently using our favorite linear solvers. But surface waves, because of this nonlinearity, are much harder to put into something that can be inverted efficiently. And the way that we can get around this is by using a method introduced by my colleague Hongjian Feng, who's a postdoc in Rob's lab. And basically, he separated out each surface wave by frequency. And for each frequency, we can calculate the depth sensitivity of that Rayleigh wave in an a priori sense, and basically project this sensitivity along the path from source to receiver and form something that's not quite a ray, but it's some linear expression of sensitivity in a way that's analogous to body waves. So we can put them in a joint inversion and solve it very efficiently. And I did this for US array data under the continental United States, and this is summarized in a paper in JGR published in 2018. And I find that indeed, by adding body waves and surface waves into this inversion, we can get a better view of the Earth than we can with either data set alone. So body waves, so with the joint inversion, we don't have the vertical smearing from body waves, but we do have sensitivity to features deeper in the mantle. And we have this clearly defined lithosphere-asthenosphere boundary at about 100 to 200 kilometers depth. So this is very encouraging that we can get better resolution within the lithosphere, but this doesn't get us closer to parsing apart thermal versus compositional heterogeneity, because we have multiple processes that we're trying to understand with one observable shear wave speed. So it's a fundamentally under-constrained problem, and the way that we can make progress on that is, well, by adding more constraints. And an obvious constraint that we can consider is VP. The problem with this is that VP is sensitive to temperature and compositions in a way that's pretty similar to VS. These are two maps taken from a model published by Brandon Schmant and Fan-Chi Lin. We have VP on the top and VS on the bottom. And we can see that they look very similar visually. So we don't really get new information by examining VP. We do note that there's maybe a few areas where they differ. It's most noticeable around the Gulf Coast in this model. So maybe if we take the ratio of VP to VS, we can sort of exacerbate these differences and find out new things. And this turns out to be a very useful parameter because it's related to the Poisson ratio, which is an elastic property of materials. So this is a figure from a paper by Ma and Lowery, who looked at continent scale variations in VP-VS ratio. And they used a technique called H-kappa stacking, which beneath a particular station gives you an estimate for crustal thickness and for a bulk VP-VS ratio within the crust. So it doesn't give you information about the mantle or about vertical variation, but it does show us that there is quite a bit of lateral heterogeneity. So we have variations in VPVS from about 1.7 to about 1.9. And comparing it with a slice at 20 kilometers in the crust from the VS model, we see that there isn't a simple correlation between VS and VPVS ratio. We have low VS and VPVS in places in the western US, but in the Northeast, we also have low VPVS ratio, but high VS. So we are looking at different properties for the Earth. So we think we can make progress in reducing this non-uniqueness of seismic wave speed if we consider VPVS. But to do that, we need a three-dimensional tomographic model of VPVS ratio as well. So the way that I retrieve that is a little bit indirect. First, I reformulate my inversion for VS to include VP as another independent model parameter, well, actually, slowness of P. So we can add P body wave phases and constrain the structure that way. But we need some independent or some additional constraint to link VP and VS together. Otherwise, they're just totally separate models. And to do that, we recognize that Rayleigh waves are actually sensitive to VP and VS, and not just VS, as I assumed in the previous paper. So if we separate these sensitivities, we get these curves. So I'm showing VP on the left, VS on the right, and periods low or shorter than 100 seconds on the top and longer than 100 seconds on the bottom. So immediately we see that for periods, even the longest periods, VP sensitivity diminishes rapidly with depth below about 100 kilometers. And this is a problem if we're trying to constrain the VP-VS ratio if we can't resolve VP. So to overcome that, we really just focus on the top 100 kilometers for the purposes of this presentation, where we do get good resolution of both model parameters, and we can still learn quite a bit about the lithosphere. So I invert for variations of slowness of P and S, and use this formulation or expression to convert it to VP-VS ratios, and this is just a chain rule expansion of this differential. So these are the maps of the different parameters in my model. We're showing VP on the left, VS in the center, and the VP-VS ratio on the right, and at depths of 20, 60, and 100 kilometers below the surface. We see that the structure of VP and VS variations broadly resemble one another and broadly resemble results that have been published previously in the literature, where we have pervasive fast wave propagation in the eastern United States and slow propagation in the western United States. VP-VS ratio does give us a little different picture. So the lowest values of VP-VS, which I'm showing in orange in this color bar, are found in parts of California and the western US. But like Ma and Lowry, we also see low VP-VS in the northeast at crustal depths. The highest VP-VS ratios are found in the Mantle at places in the west, and I want to note that the highest values are found beneath the Yellowstone hotspot and the Rio Grande Rift here, and these are areas where we observe high heat flow and volcanism. So if we're going to have partial melt anywhere beneath the North American lithosphere, it's going to be here, and this is consistent with that because melting and the presence of fluids decreases both VP and VS, but especially VS, driving this ratio up. So visually and intuitively, these results make sense. And now that we have a tomographic model, I'm going to go on to the next part of this talk, which is comparing our seismic model to this forward modeling from geochemistry. So now we're looking at this half of our workflow. And in order to calculate seismic velocity from geochemistry, we use a toolkit developed by Billy Shinovar, along with Ali Agutz and Mark Bain. And this is the Whole Rock Interpretive Seismic Toolkit for Ultramafic Lithology, also known as WISTFul. And I helped a little bit in coming up with this acronym name, and I think that might be one of the things that I'm most proud of from all of my PhD. So WISTFul contains a database of nearly 5,000 mantle rock compositions, and these are taken from real rock samples, mostly compiled from the EarthChem and GeoRock databases. And they're described in terms of their major element oxide weight compositions. So Billy, from these compositions, uses a software called Perplex to find which minerals are stable at a given temperature and pressure condition. So it'll report things like how much olivine, how much orthopyroxene is the aluminous phase spinel or garnet, things like that. From that, we can use estimates of the elastic moduli for these end-member minerals and get bulk estimates of moduli such as the bulk modulus, the shear modulus, and we can also do a similar thing for density. I want to add also that we do a correction for anelasticity at higher temperatures here. So from these moduli and the density, we can then get estimates for seismic velocity. We can get VP, VS, and my favorite VP-VS ratio. And we now have a quantity that we can compare directly to my seismic model. And the real benefit of developing my inversion alongside Billy running the forward modeling is that we were able to compare preliminary results and look at the intermediate steps and really make sure that we had a tight workflow that shows agreement. So first, I'll plot some results from the Wistful toolkit. These plots will be in the space of VP on the x-axis and VP-VS ratio on the y-axis, and I'll return to views like this later on in the talk. So each of these dots is one of two rock compositions at temperatures ranging from 300 to 1100 degrees C, and the two rocks are distinguished based on a quantity called magnesium number, which is the magnesium content relative to the total magnesium and iron content. So how much of this depletion process has been going on. So we have an enriched composition, which means enriched in iron, and also aluminum and some other things. So this has a low magnesium number. And we've also run this calculation for a depleted, an iron depleted composition, which then will have a higher magnesium number. And we can make two observations about these results. Firstly, that the slope seems to change after about 800 degrees Celsius, and that's where anelasticity begins to be important. The second observation is that in this low temperature elastic regime, a change in temperature is associated mostly with a change in VP, indicated by this arrow. So the effect of temperature on the VP-VS ratio is almost negligible. So this means if we do see a variation in VP-VS, such as caused by magnesium and iron substitution, we should be thinking that we need to invoke a compositional change to explain that. So this is the forward modeling, and the first thing we tried to do in comparing the forward modeling and the inverse modeling was just to plop them on top of one another and see what they said. So each of these black dots corresponds to a point from our seismic model at 60 kilometers depth, and I'm only plotting points within the US and Canada on land. And right away we see that there's pretty good agreement in terms of the span of possible VP from both of these modeling. So 300 to 1100 degrees seems to explain most of the VP in the North American lithosphere. We note that the difference in VP-VS ratio from our enriched to depleted peridotite examples can account for nearly half of the total variation that we observe in the VP-VS ratio. And this is important because this tells us that these are distinguishable in our seismic model. So we can make claims about what the compositional variations are, and we can use this VP-VS parameter to help us constrain composition. So ultimately, we want to move from this comparison view and really go to a state where we can match temperature and composition at each point in this model. But first, to do this, we want to make sure that the layout and where these points from the seismic model correspond to make sense geographically as well. And to do this, we perform a clustering analysis. So we divide our model into 10 different clusters using a k-means clustering algorithm. I'm actually only showing 9 here because one of them only included points in areas of poor resolution. So these clusters were assigned only seeing VP and VP-VS ratio, so there's no geographic information in them, but we find that they correspond very well to geologic settings and show geologic agreement. And I can add some boundaries of these Proterozoic and some younger provinces, and I hope I can convince you that there is geologic meaning behind where these clusters are. So the color that I've chosen for these clusters is such that the cooler colors describe high VP and the warmer colors describe low VP. And looking at this map, we can see that the eastern US is all blues and purples and greens, and the western US is all these warmer colors. So this striking contrast between the east and the west is described really by VP, and VP-VS ratio is sort of a secondary constraint on this first order structure. But it is necessary, I want to point out, within the Wyoming province here, which is one of these Archean cratons. We have very little change in VP, but quite a big change in VP-VS going from north to south across the region. So both model parameters are important and are necessary to tell us the structure. So now I can fit our best estimate of temperature and magnesium number across the entire seismic model at this depth slice. And I determine temperature and magnesium number using sort of a grid search, where I run through all possible composition and temperature possibilities and select the ones that give the lowest misfit for the 100 best fitting compositions. So from this, I get an estimate for the misfit, which is what I call the fitting error. For the most part, across the United States, we have a pretty low error of less than 0.5%. There are some places where error is higher, and I've graded these out on the other maps. This plot here just shows the standard deviation of the magnesium number from this estimate. And I want to note that the areas with high error are not random, and they seem to be associated with these regions that might contain partial melt that I pointed out before. And to test this, I plotted in these red triangles, I hope you can see them, the locations of volcanoes that have been active in the last 10,000 years. And this, so these are where it's feasible that we could have partial melt because we have magma. And we see that these agree pretty well with the areas of high error. So this shows us that the main source of error in our wistful fitting is partial melt that we're not accounting for in the forward modeling right now. So I want to make a few first order observations about these structures. Firstly, we can see that temperature varies widely from about 300 to about 1100 degrees Celsius at this slice of 60 kilometers. And in general, we have cold temperatures where we observed fast VP and warm temperatures where VP was slow. So this first order structure of hot and cold, or of fast and slow, is really dominated by hot and cold. So the assumption that seismologists like to make, that temperature is the main control on seismic structure, on these large continental scales is approximately true. At least our results agree with that. And in the magnesium number, we don't see this pervasive pattern of west versus east. There are specific regions where magnesium number is lower, but for the most part, we fit a magnesium number between 91 and 92, which is about what we would expect for a typical sort of depleted but not super depleted continental peridotite. So some of the areas where magnesium number is lower corresponds to regions such as, or corresponds to these high error regions where we think there's partial melt. But there are also regions where this shows us geologically meaningful information. So these anomalies that I've listed as 1 and 2 correspond to areas where the crust has been observed in independent studies to be thick. In which case, at 60 kilometers, we might actually be sensing the crust. So we're not fitting mantle rocks at all, so we can't really explain these anomalies using magnesium number. The other regions that I want to point out are this area that I've notated 4, which is in the Wyoming province, which I already noted had variations in VP/VS ratio. And we fit a lower magnesium number of about 88, 89 in this area. And refraction studies from the 90s indicate that there's a high density layer of something with velocity higher than the crust below the crust in this area, which they attribute to underplating of material coming from melting somewhere deeper in the mantle. So this is consistent if we assume that that will have a enriched iron composition or depleted magnesium number, so this is consistent with our results. We could then invoke a similar explanation in this anomaly marked number 3 here, where we have iron enrichment. And I want to point out that this aligns with the outline of the Midcontinent rift, which I mentioned earlier. So this will be the focus of the last part of my talk. So the Midcontinent rift is sort of what we call the geophysical geological anomaly associated with the confluence of 2 major events about 1.1 billion years ago. First, there was continental rifting. So the lithosphere started to split apart, similar to what's happening in East Africa today. And for whatever reason, that shut off and didn't continue. There is also a plume, which is termed the Keweenawen plume, which passed beneath at the time. So this anomaly is noted as a very strong positive gravity anomaly. So the force of gravity, if you're standing over this, is higher than what we would expect otherwise. And there have been a lot of studies, geophysical, geochemical, and we have a good first order idea of what the structure of this region. Really instrumental in this understanding is the glimpse active source arrays, which were run over Lake Superior in the 1980s. And this is the model introduced by Seth and Carol Stein in a 2018 paper. And they show kind of a classic rift basin structure similar to East Africa today, filled with a lot of volcanic rocks, and that's really what causes this high density signature. But there's also this dense lower crust layer that they put in. And in fact, it's not really lower crust, but it's some material at the base of the crust that they attribute to then underplating of mantle material from this plume. But to verify this, we really need to be able to see the geochemistry of this anomaly, but it's 40 to 60 kilometers below the surface, so it's not entirely possible to sample that. But we're hoping to use this combined wistful and seismic interpretation in order to see if we can detect changes in the geochemistry due to this layer. And just a reminder of the processes that might cause a chemical anomaly. They can be due to iron and magnesium differences from melting, or due to silica addition due to metasomatism. And this sort of plot is the tool that we'll use to diagnose these different chemical processes. And this is a complicated plot. It's by a review paper from Cindy Lee looking at forms of cratonic alteration. And we don't need to pay attention to everything that's going on here. The main point is the x-axis is total iron content. The y-axis is total magnesium content. And these are both parameters that we can derive from our wistful modeling. And all of the scattered points just correspond to a sample that has been taken from mantle peridotite xenoliths, so rocks from the mantle that have been found near the surface. And these 2 trend lines are really the important takeaways from this figure. So this green line is labeled refertilization. So this is the direction that something being enriched in iron at the expense of magnesium will take in this mineral space. Iron depletion would go in the opposite direction. Meanwhile, silica enrichment due to metasomatism will deplete the relative contribution of both iron and magnesium, so it'll move closer to the origin. So with this in mind, let's look at the seismic model beneath the Midcontinent rift. So this is VP/VS and VP/VS ratio at a slice at 50 kilometers depth. We see an increase in VP/VS, a decrease in VS, and some lower VP anomalies, but it's not very convincing compared to the other parameters. So this immediately tells us, firstly, that there's some sort of lateral heterogeneity within this anomaly. So we want to focus on these 3 areas that I've circled, and these are based on where we have strong low VS anomalies. So here's them again without the background model. And I want to note that where these anomalies occur seems to correspond to where the rift axis intersects these black lines, and these black lines are the boundaries of the major Archean and Proterozoic terrains that comprise the lithosphere. So we have the Superior, the Panochian, and Yavapai provinces. This line here is basically the Archean Proterozoic boundary in time, represented in geologic space. So I'll return to that a little bit later, but now I'm showing where these points fall in the VP versus VP-VS space. The highest VP is observed in the northern anomaly. The highest VP-VS ratio is observed in the central anomaly, and the southern anomaly is lower in VP and in VP-VS. And now we estimate magnesium number based for each of these clusters of points. And we do this at a single temperature for each anomaly, which we derive from those continental scale maps that I showed earlier. And the color corresponds to the magnesium number. And we see that there's a spatial trend in MG number along the Midcontinent rift. The lowest magnesium number is found in the central anomaly. The mean value is about 89.2. In the north, there's a slightly higher magnesium number of 90, and the south has the highest magnesium number of 91.6. The uncertainty on this, just based on the standard distribution, is about 0.8 for all of these. So this difference between the north and the south is a robust difference that we detect. And I want to note that in another part of my thesis, which I don't discuss here, I estimated the mean magnesium number for the entire Superior province, and a sort of average value is 91.2. And this is comparable to the value that we found in the southern province. So we don't have evidence that there's any geochemical difference or any strong geochemical anomaly in the southern part of the Midcontinent rift. So we want to look at these anomalies in this view that can tell us about the chemical processes happening. And as we suspected, the southern anomaly plots kind of at the base of this refertilization trend. So this is what we'd expect from typical sort of depleted continental lithosphere. But as we go to the north and then to the central, we go along this trend towards increasing fertilization, towards increasing iron content. So what this could suggest is that we have 2 components, sort of typical continental lithosphere, and a deeper fertile source may be coming from a more primitive mantle source. And they're mixing, and this fertile mantle component is the strongest in the central part of the anomaly. So what do these observations mean? Firstly, our observation of iron enrichment below the Midcontinent rift is consistent with the model from the Stein papers, suggesting that there's iron-rich underplating at depths extending to about 55 or 60 kilometers depth. The second is that there's lateral variation in this feature, and that there seems to be some correlation between where these anomalies are prevalent and suture zones within the lithosphere. So I'm suggesting that these seismic anomalies are showing us things about how the mantle plume interacted with the lithosphere. So these suture zones, we can imagine that there were big dramatic collisions. Maybe there's pieces of oceanic lithosphere. There could be different hydrated mineralogies which weaken the rocks. And these might be exploited by the mantle. So this is showing some kind of these major conduit systems with locally thickened places of melt. So maybe that's what we're observing beneath the central Midcontinent rift, is more melt that's been frozen in that's associated with some conduit that's exploiting lithospheric weakening. So in another part of my thesis, which again I'm not going into detail about here, I look at a feature called the Great Meteor Hotspot, which is another plume that passed below the North American lithosphere, not far from the Midcontinent rift. And this is expressed very differently. I didn't find any evidence of chemical modification of the lithosphere, at least when it was below the Superior Province, which tells me that there's something special about the Midcontinent rift that allowed this big chemical anomaly to be put in place. And I suspect that that's because there is ongoing tectonic extension, and the magma from the plume was able to permeate the lithosphere a lot better than it could in sort of this stable Archean non-tectonic regime. So with that, I'll give a summary of what I've discussed and move on to some conclusions. So this is the framework I presented. We've combined inverse modeling of seismic data with the forward modeling of geochemical and thermal information, and compared them at the level of seismic anomalies, and found that we do have agreement and that we see interpretable variations that can help us understand the relative effects of thermal and chemical behavior on the lithosphere. So my first question that I posed at the beginning was, what controls seismic wave speed at large scales within the lithosphere? And the answer to that is temperature to a first order, but there are places where compositional variation is required and where that can teach us things about the Earth. The second question is, how is cratonic lithosphere altered over geologic time? And my sort of answer is that, well, this is very hard to do. And when it does happen, it does it in a way that's very dependent on the tectonics at the time and on the history of the lithosphere. So if I can expand on this idea just a little bit, the Archean lithosphere, it's old, it's cold, it's thick, it's generally resistant to modification. So if there are pre-existing weaknesses, such as ancient suture zones, those can be more easily exploited and more easily deformed, and that's really what governs how the lithosphere will evolve. So we can think about this in sort of supercontinent timescales. This figure shows the configuration at the end of Pangea of part of Gondwana, where we have modern South America, Africa, and India just chilling together. And these cratons, the black lines represent dike swarms, so that's where the rifting initiated during supercontinent breakup. And they happen between the margin, or between these cratons. So the areas where that act as collision zones also act as the regions where rift is initiated. So history really matters, and the areas that have been deformed in the past deform in the future, and the cratons can sort of keep on keeping on. So I'll just mention a few future directions for this work. The analysis that I've performed was at a very large scale, and we made a lot of assumptions in order to make these global and continental models. So we ignored things like attenuation and azimuthal anisotropy. But if we're trying to look at a smaller scale feature or need a more accurate estimate of velocity, we might need to take these into account and maybe use a more sophisticated nonlinear inversion. From the petrologic side, there's a lot of improvements that can be made. Just a few examples of directions that can go is adding the ability to model more hydrous phases and the effects of partial melt, and that can allow us to examine different tectonic settings and look at things like mantle plumes that are active today. But the most important thing that we can do probably is just to add more data. And for those of you who were at Frederick Simmons' talk last week, he made a compelling argument that data resolution and coverage is really still a lot of the limiting factor in what we can understand about the Earth. So if we can put in more US arrays on other continents, we can put seismometers at the bottom of the oceans, we can really start to illuminate more of the Earth. So finally, we all sort of have our fantasy projects where if we have unlimited resources and technology, what we would like to do. So I noticed a proposal put forward by Randall Munro, who's the author of the XKCD webcomic, and he suggested continuing to split the Midcontinent rift. And I think it would be really interesting to observe this feature in real time. So why not? Okay. Yeah, I did have I did have a few acknowledgements and thanks that I wanted to give before this talk gets too silly. So first I want to thank Rob, my advisor. It's really been a privilege to work with one of the giants of seismology in terms of his reputation, but also like literally. Also thank you to Hongjian Feng, a postdoc here today, and also Scott Burdick, who is a former student of Rob, and both of them put in a lot of really hard work that I sort of based my research off of, and they also provided a lot of extensive advice, technical help, and this work wouldn't have been possible without them. I also want to thank Billy, and as well as Ali and Mark, kind of on the wistful side of my of this project. Their work really allowed me to sort of connect my research to the Earth and answer the geologic questions that I wanted to address all along. So I'm really glad that we could have this collaboration. I also want to thank the rest of my thesis committee, Wiki, Brad, Fiona, for asking the hard questions, but also encouraging me. And I have a long list of co-authors and collaborators to make models of the Earth at global scales. It's really helpful to have a global network of researchers who are openly sharing data and ideas, so they make this science happen as well. I also want to thank the administrative staff of EAPS and ERL, and especially Josh Kastorf, who's setting up this live stream today. And I also want to thank my lab mates and everybody in the ERL buddies, the lunch crew, the peer hour crew. It was just really an honor to come to work every day and work with like such a great group of people from all different backgrounds and learn about science, but also have a lot of fun along the way. I don't know if I'll be this lucky again. I have more pictures, but I'll go through them quickly. Just want to thank my parents.
This is your opportunity.
My parents, my roommates, Lindsay, Deborah, Sarah, Kasturi, Panda the cat, the GSC officers, friends from high school, friends from college, and everybody else. You've really made this journey enjoyable, and it wouldn't have been possible without you, so thank you.
Well, it's clear Eva has had a lot of support from high school on through graduate school, so I think maybe not so many people are as lucky as you've been to have such a great group of friends and colleagues. For now, we are going to take a 5-minute, questions from the audience, and then after that we'll take a 5-minute break, and then the committee and Eva will reconvene. So questions that are not from the committee.
Tom?
I'm curious, Eva, you have a forward model coming into the middle, an inversion coming from this side. Have you decided to think about going from the seismic waves straight over to the meteorology, to the mineralogy?
Yeah, there are a lot of researchers who are doing workflows like that, and like that's a valid option. I guess the problem with doing that is that they have to make a lot of simplifying assumptions about the controls that the chemistry has on the seismic wave speed. So that, because in order to get it into an inverse framework, you have to make sort of empirical guesses about what those are, but those really can't account for things like the Garnet-Spinel transition, which is really gradual and complicated and affects the minerals around it. So I guess this gives us a more nuanced way to look at the rock side of things.
Other questions?
Uh-huh.
Well, Eva, that was awesome.
Thank you.
I was wondering, you showed that some of the places in the west near the potential melt bases, they were kind of breaking down, you weren't minding to fit in the low VS bases. You said it didn't fit so well the wistful toolkit.
So like these here?
I was wondering, is there any potential in the low VS bases that what's happening is something to do with the Q model you're choosing that is affecting the
Yeah, so I'm ignoring attenuation. So I don't, in this linear inversion, we don't really have a way to account for that property. So I mean, that could definitely, the not accounting for that could be a source of error for sure in this, yeah. Did that answer your question?
Anyone else?
I'm not that good with the geologic side of things. I'm just wondering, 85 to 92, is it a big spread or is it not big, or is it
85 to 92.
in an easier ratio?
Yeah, I mean, I guess so. These are all rocks that have been observed. So like they're all realistic ranges, but that is large and it's much larger than the error around it. So yeah, I would argue it is geologically significant. Deborah?
I apologize for if this is an incredibly naive question, but you have spots of high error on the east coast, which are unrelated to volcanic activity. Do you think that those are spots of melting that were unrelated to volcanoes?
That's actually a really good question, and I promise, like, we didn't plant this.
Plants.
No, she is the plant expert here. Yeah, so for example, well, so for these spots up here near Maine, like this is just, we don't have very good data in this area. For this part in particular, in the Appalachian Mountains, there actually are some studies done by seismologists who do think that there's sort of one of these little asthenospheric upwellings, not really a plume, but hot material closer to the surface. And some of these papers, so things like Maureen Long's group out of Yale, does argue that there could be partial melt here. So it's interesting that we do see a similar kind of, that our model errors out in the same way in this area. So maybe that's a consistent pattern behind melt, yeah.
Okay, good. Well, thank you all for coming. Thank Eva one more time.